This is a video of ink separating from water. There's nothing physically impossible about this situation. This is a thing that could actually happen, but still, we never see it happen. And by the time I was done with the first sentence of this video, you'd probably already figured out that I just reversed the footage. In this case, I reversed a clip of the ink machine from my last video. But why do you know that? Why do humans have an intuition for what direction time should move? Here's another example. Two rolling steel balls colliding with each other. I'm playing the same clip forwards and backwards here. Which do you think is playing forwards and which do you think is playing backwards? This one is a lot harder. Entropy is a complicated thing, and if you take nothing else from this video, remember this example with the colliding steel balls. In this interaction, where two particles collide, there is nothing physically preventing both of these interactions from existing. In fact, if you played this clip one way, then froze time, reached into the system, reversed the momentum vectors of both balls, and click play again, it would play out precisely in reverse. But let's look at a more complicated system. This time we have 10 particles interacting, 5 black and 5 chrome. It looks pretty normal. Then all of a sudden, all the black and chrome balls end up on opposite sides. That seems really weird. And if you're thinking that's weird because this clip was reversed, you'd be right. This clip was reversed. This is actually the start of the video. Playing forwards now, I started the balls in two distinct groups, and then agitated them so that they would randomize. Pretty quickly, the order of the starting condition fades into this disordered mess. But what about this clip? Now there are balls bouncing all over the place, just like before, and then look at this. All the colored balls end up on one side again. This clip is not reversed, but it took me hours of work to create. I started the balls in a random configuration, then I mixed and mixed and mixed and mixed until they all ended up separated again. I had to wait for luck to be on my side. We're going to come back to this example in a little bit with a more detailed analysis, but remember the condition with all the balls on separated sides isn't impossible to generate by random chance. It's just really, really unlikely. It's much more probable for a system to evolve from ordered to disordered than for an equivalent system to evolve from disordered to ordered. When we make the leap to systems with large numbers of particles, like the 10 trillion water molecules visible in this example, the unlikely options, like all of the ink and water separating from each other, are so unfathomably unlikely we can reliably say that they never ever happen. Entropy is one of the hardest to understand concepts in physics because there's nothing like it that we interact with in the macroscopic world. The second law of thermodynamics, that in isolated systems entropy will always increase, is less of a physical law and more of a statistical one. Like, you won't win the lottery every day for the rest of your life. If anybody watching thinks that it's possible, like, not even likely, but possible for you to win the lottery every day for the rest of your life, then you're not going to enjoy thermodynamics. In a few minutes, after we have a working definition of entropy, hopefully you'll see that this becomes a rather circular argument because the most likely outcomes are defined to have higher entropy. So I'm not kidding about the statistics. You can define a useful definition of entropy by flipping coins. And that definition is going to end up being completely equivalent to the example with the balls, and even equivalent to the example of ink mixing with water. It's going to take some doing, but I hope that by the end of this video, you have an appreciation for why entropy has to increase, how it can do work, and why it has some very strange units. But first, we're going to take a detour for 5 minutes and 27 seconds and flip some coins. And then we'll come back to reality and we'll look at the ink tube and an actual demonstration of osmosis. So imagine that we have, whoa, we don't need that many yet. Imagine that we have 4 coins and we flip each of them. Tails, heads, heads, heads. So we got 1 tails and 3 heads. That's not the most likely option, but it is a likely option. When we flip 4 coins like this, there are 16, I don't have 16 fingers. 2 to the 4. There are 16 possible outcomes, and each of those possible outcomes is equally likely. Notice that there's only one way to get all tails, and one way to get all heads. There are 4 outcomes where 1 coin is tails and 3 coins are heads. There are 4 outcomes where 1 coin is heads and 3 coins are tails, and there are a whopping 6 different ways to flip 4 coins and have 2 of them come up heads. When you flip 4 coins, the most likely outcome is that 2 of them will be heads and 2 of them will be tails. You don't know which 2 of the coins will be heads and tails, but that doesn't matter. You have a 6 out of 16 chance of selecting one of these states. I'm holding off the rigor here for a few minutes. Thermodynamicists in the audience, don't get mad. I'll fix it. But for now, let's say that the entropy of this system is 4, the likelihood out of 16 of getting 3 heads and 1 tails. If I flip all these coins again, now we got 2 heads and 2 tails, which conveniently is the same thing that I wrote in the script. The entropy of this system has changed. The entropy of this system is now 6, because there are 6 out of 16 possibilities that give us 2 heads and 2 tails. Entropy is not a conserved quantity. There's nothing wrong with me reflipping the coins and saying, oh, the entropy is different now. You can keep flipping the coins and keep updating the system, and the entropy will keep changing. So now let's upgrade to 10 coins. This means I need to expand my spreadsheet, because now there are 1,024 different outcomes for this experiment, but only 10 possibilities for the sum. We can't flip 10 coins and get more than 10 heads. So now our distribution looks like this. Unsurprisingly, the most likely outcome for flipping 10 coins is seeing 5 of them turn up heads. In fact, there are 252 different ways for that to happen. But what about a situation where only 1 coin is heads? Of course, because any of the 10 coins could be that 1, there are 10 different ways for that to happen. If we've got 10 coins, this one could be heads, or this one could be heads, or this one could be heads. There are 10 different ways for that to happen. Another way to think about it is permutation. So instead of flipping them, you can go, well, you know, that one could be heads, or that one could be heads. And the rearranging definition is going to be the one that's a little more relevant for mixing, but mathematically they're equivalent. You can just keep flipping coins. Entropy is commonly referred to as disorder or randomness. But these terms are pretty biased by our human intuition for what it means for something to be sorted or ordered. Out of these 1,024 possible arrangements of coin flips, which of these feels more likely to you? All tails, or heads, heads, tails, heads, tails, heads, 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 tails, tails? I'll give you an intermission to think about it. That's a trick question. Both of these patterns are equally likely. You could flip coins for a very long time and not flip 10 coins and get a string that was heads, heads, tails, heads, tails, heads, tails, tails, heads, heads. But ask yourself, did you notice that during the break I actually flipped all 4 of these coins? While flipping 10 coins and getting all tails and getting this particular sequence are equally likely, getting all tails is significantly less likely than getting a sequence that sort of looks like this one. Humans like to see patterns, and that has led us to this definition of entropy where stuff like this is said to be disordered or to have a lot of entropy. The way we quantify this is to add up the results. In this particular case, we have a sequence with 6 heads and 4 tails. There are 210 different ways that we could have flipped 10 coins and gotten 6 heads and 4 tails. But there is only one way to flip 10 coins and get all tails. This pattern has more entropy because there are more ways to make a similar pattern. So what's the scoop with the second law of thermodynamics? If entropy is just this unconserved quantity and it's free to go up and down and do whatever it wants, why do we see the entropy in closed systems or the entropy of the entire universe going up all the time? Why doesn't it ever go down? Let's look at a very skewed version of the coin example. If we have a system of 2 heads and 8 tails, there are 45 ways to achieve that outcome. Out of that big list of 1,024 options, 45 of them have 2 heads and 8 tails. So I just reflipped all the coins, and I could have gotten the state where I flipped 10 coins and got all tails, which would have had our fake entropy measurement of 1 out of 1,024. But I didn't. I got a state with, 4 heads and 6 tails. If I had flipped 10 tails in a row, the entropy of the system would have decreased. Like, there's nothing wrong with that. It's totally legal. I can physically flip a coin and get a tails, so I might as well be able to do it 10 times in a row. But it's not very likely. It's significantly more likely to have gotten a setup like this with 4, 5, or 6 heads in the sequence, because there are a combined 672 ways to achieve one of those outcomes. Let's return to the balls for a minute. We can map this system directly onto our coin example. If we have a chrome ball on the left side, that's like flipping a coin and having it come up heads. If we have a chrome ball on the right side, that's like flipping a coin and having it come up tails. If we reverse these definitions for the marbles that I've Sharpied black, then this arrangement is equivalent to flipping 10 coins, having 7 of them come up tails and having 3 of them come up heads. If they separate completely like this, that's like flipping 10 heads. Or if they separate completely like this, that's like flipping 10 tails. As these balls bounced around, I filmed the whole thing, and then I fed 24 minutes of marble footage into a script I wrote that took most of a day to track all the balls and calculate how likely various configurations were. For each frame, it finds all the balls, figures out which color is which, figured out which side of the line they're on, and does the math to calculate a score that maps the current configuration of balls onto the coin flipping model. Even though I was standing there watching the whole time, I only actually saw the balls sort once while watching live, but it actually happened 6 different times for a total of a whopping 56 frames of video. Let me say that again. In 24 minutes of bouncing, the balls were completely sorted in either direction for less than 2 seconds. This is not a very likely outcome, and the unlikeliness of that outcome is extremely well predicted by the coin flipping model. Here's the distribution of coin flip probabilities, and here's the data from the ball tracker. Almost identical. One of these plots was generated by adding up all the possible ways to flip 10 coins, and the other was generated by watching balls bounce for half an hour and analyzing their motion. And they're the same. Math is so satisfying when it works. So now let's zoom out. What if we were flipping 100 coins, or 1,000 coins, or 10,000 coins? I had to simulate these instead of solving for every possible solution in Excel, but as you can see, the larger the system gets, the tighter the distribution of probable outcomes. If we have a system of 10,000 coins, and 3,000 of them are heads, the next time we flip all those coins, we are basically guaranteed to have a near 50-50 ratio of heads and tails. It's so unfathomably unlikely to get 3,000 heads and 7,000 tails that it just won't happen. This tube of water, a real system of particles in the real world, has about 10 to the 25 particles in it. These kind of huge numbers make probabilities into certainties. I mean, that's why the second law of thermodynamics is referred to as a law. There's no thermodynamics police force. Like, literally, there is no fundamental force of physics that causes systems to increase in entropy, but you will never witness a large system break the second law of thermodynamics. It sounds really circular when stated like this, because I'm basically telling you that entropy increases because the high entropy states are most probable, when the definition of a high entropy state is that it's very likely to happen. But that's basically it. I mean, that's why it's confusing. It's just human nature that these very probable states also tend to look messy and disordered. The crazy thing, to bring this back to reality, is that energy, which is a pretty tangible thing, and entropy, which is pretty obscure, are loosely interchangeable. You can actually store useful energy that can do work in the real world in a system that is ordered. Like, the order itself sort of stores energy. Okay, now back to the real world. This is a tube filled with water. If I pour water in one side, the water inside sloshes back and forth until the level on both sides is the same. This is because gravity pulls on the water in this tube and gravity pulls on the water in this tube equally. If at any moment the water level in one side is higher, there's more total force there and it falls back down and equilibrates. This is another tube filled with water, but it's a little more complicated. On the left side, I've just filled up the tube with tap water, but on the right, I've filled the tube up with water mixed with sugar. In between, at the bottom here, I've inserted a membrane that lets water pass from one side to the other, but not the sugar. If you want to, you can think of this just like the marbles. One side has chrome balls, one side has a mixture of black and chrome. The chrome ones are allowed to go from side to side, but the black ones are trapped on the right. In the regular tube of water, gravity pulled down and the water ended up equalizing, so the water on both sides is at the same height. In this case, you can see that I started with more water on the clear side than the sugar side. But because the sugar water is denser and heavier, I think the two sides were actually close to balanced at the start. That means that it's pretty weird that at first the sugar water side goes up despite being heavier. For some reason, we're moving water through the membrane from left to right. Even once the water level on the right gets higher than the left, the water keeps pumping. This system is doing work. It's lifting water against the force of gravity. And the only thing driving this process is the fact that the water over here is pure and the water over here is mixed with sugar. This process is called osmosis, and it's weird, like really, really weird. So where's the entropy? As I complained in the last video, water is clear, which means you can't actually see what every water molecule in the tube is doing. So let's repeat this experiment at marble scale, and then we'll do some math to try to quantify what we just saw. On the left, we have a pure substance, just water. But on the right, we have a very concentrated solution. Lots of solute, ink, water, whatever, and less water. Unfortunately, I don't actually have a color-sensitive marble filter, so I'm going to be doing this by hand and speeding up the footage later. But I swear I'm trying to agitate the marbles as uniformly and unbiasedly as possible. As I shake the border, the marbles move around. Every time that a chrome marble passes the center line, I let it through, and every time a black marble tries to cross the center line, I turn it around as though it hit a wall. You probably can't notice it in real time because I'm using a very small enclosure here, but there are, on average, actually more balls on this side at any given time. I reran the same tracker script from before, threw out any frames obscured by my hand, and found that the average distribution wasn't 10 balls on both sides. It was more like 10.7 over here and 9.3 over here. There are two opposing forces at play. First, and more obviously, is the effective pressure. Collisions between balls are trying to evenly distribute all of the balls, spreading them out so it would be 50-50. There'd be 10 on one side and 10 on the other. But we also have this entropic effect, where the chrome balls want to spread evenly to both sides and the black ones can't. If I made the bounding box really, really big so there were no collisions between the balls, you could imagine that on average the 15 chrome marbles would spread evenly on both sides and the 5 black marbles would still all be on one side. In reality, we get something somewhere in between these two extremes. Weirdly enough then, this means that chrome marbles concentrating on one side is actually the most probable outcome. So what does it mean to be a mixture? Well, if you have a mixture of two particles, they're free to move around and swap places with each other. So we have to consider all possible permutations of a set of particles. Hey, that kind of sounds familiar. So let's do the same math as before, but this time let's put different amounts of solute on both sides of the system and solve for the entropy on both sides independently. On the left, we start with 1 black marble and 9 chrome marbles. Then on this side of the membrane, we have 10 different ways to arrange our particles. On the other side, we have 6 chrome marbles and 4 black marbles, and there are a lot of ways we could mix these particles together. 210 different ways, in fact. Now we've got this membrane between these two groups that the chrome balls can pass and the black ones cannot. So what happens if we take a chrome ball from either side and cross the membrane? If a single chrome ball passed from right to left, we would add a tiny bit of entropy to this side, because now there are 11 places to put our solute particle. But we've massively decreased the entropy on the right, from 210 down to 126. There are many fewer ways to rearrange this system after you remove a single chrome ball. This change has made the entire system more ordered. We're sorting the balls, and it results in a total decrease in entropy. But what about the other way? If we take a chrome ball from the left and move it to the right, we slightly decrease our options on the left, down to 9 from 10. But there are now oodles of arrangements for balls on the right. We started at 210 possible arrangements, and the addition of one more ball takes that all the way up to 330. So at this point, through excruciating counting, we have determined that the system with more mixed marbles has more entropy. It's more likely. But what in the real world actually makes this happen? Why does the system evolve? It happens because of random fluctuations, thermal fluctuations. When you get down to the scale of atoms and molecules, everything's vibrating and zipping around with thermal energy all the time, just like these marbles, because everything's hot. And if it's hotter, it actually randomizes better. So in the example with 20 marbles, we had the two competing forces. Pressure was trying to make them 10 and 10, but entropy was trying to significantly skew that result to one side. If the marbles were bouncing faster in a wide open space that let them really zip around and randomize, we would be biasing that system towards the more entropic result. Higher temperature actually allows entropy to do more work on a system. More temperature results in more atomic scale jiggling, which results in more randomization, and eventually more energy output from the randomization of the system, because the hotter it gets, the more you randomize it. In the case of the water column in the osmosis experiment, the energy was used to push water up against the force of gravity. To make some very hasty approximations, this sugar water has a density of about 1.3 grams per cc, and it went up by about 1.5 feet. This tube is about 1/2 inch in diameter, so it took about 170 millijoules of energy to lift this water this high. And we did this at room temperature, about 300 Kelvin. That means that in the process of adding pure water to the sugar water that was already here, we created about 6 times 10 to the minus 4 joules per Kelvin of entropy. That entropy, joules per Kelvin, implies that if the water temperature were higher, the same amount of added disorder could actually do more work. If I heated this system up, the water would actually lift up higher. Not because of the density or gravity or anything like that, but because the molecules near the membrane at the bottom would be shaking faster and randomizing more. Now, before we wrap up this video, I need to come clean to all the thermodynamicists in the audience and say that the numbers that I've been using as entropy, the likelihood, if we've got, 1,024 options to flip all these coins, the numbers that I've been calling entropy are actually multiplicities of the system. Every possible arrangement of this system is known as a microstate of the system. And the number of possible arrangements that exist without flipping any coins is known as the multiplicity of the system. So the number that I've been reporting as entropy is actually the multiplicity of the system. In order to get the real calculable entropy of a system, you need to find the macrostate of the system, or at least the multiplicity of that macrostate, the likelihood that you get a similar outcome. You need to take the natural log of that probability, and then you need to slap a Boltzmann's constant out front. This means that in the marbles doing osmosis example, where we were calculating the entropy of two different systems that were sort of part of the same system and then adding those entropies together, we actually needed to calculate the likelihood of each of these systems as a multiplicity, then take the log, then add those logged values together, which complicates the process a little bit, but it doesn't change any of the results that I talked about. It's a little less cut and dry as a demonstration because you've got to do more math, but if you do this math for a very large system, you can basically predict the future. If you can find the highest entropy state for a system, you can reliably say the system is going to approach this state given enough temperature and enough time. You don't need to know how every individual particle is going to bounce. You don't need to be able to observe every interaction between water molecules and ink or sugar or something at a membrane and solve for all that physics. You just need to be able to take gross probabilities and you can predict reliably the evolution of the entire system. It actually gets more accurate the bigger the system is. And for ridiculously huge systems, like, a cup of water that you're stirring some sugar into, you can be darn sure that it's going to find its highest entropy state if you give it enough time and enough temperature, simply because that's the most probable thing for it to do. So now you, like me, are probably wondering how this script got so bloated, and where's the ink machine again? So, I'm sorry, but entropy is cool. Actually, it's not cool, it sort of relies on heat. In the last video, I built this contraption that mixes ink and water together in a clear tube, and it looks really cool. That was kind of the point. I spent a whole video talking about how it lets us observe fluid dynamics in a pipe, but I didn't talk about the most interesting part, the title. On the front here, I wrote entropy of mixing, and that is the increase in entropy that results from combining ink and water in this way. And the coolest part of this entire project is that it happens in reverse. I'm actually separating the ink and water so that we can mix them again. That's what's happening inside this filter cartridge at an extremely high pressure. Ink and water are going in at about 100 psi, and pure water is coming out the other side. So how does this work? Well, In this demo I did earlier, we took pure water and mixed it with sugar water. And we saw that through the process of osmosis, this system was actually able to do work by increasing entropy. We were mixing two substances together, creating entropy, and from that, actually extracting energy in the form of pressurized water that could lift to a higher height against gravity. If in this example we were able to put like high pressure air or something into this tube, we could actually backdrive this entire system. We could force water and sugar to separate through this membrane, giving us pure water on the other side. The side effect here is that we can't actually get rid of the sugar, so the mixture in this tube would get progressively more concentrated. We'd effectively be squeezing pure water out of, like, syrup. And when we do this, we would be sorting the system. We would be decreasing its entropy, putting all the water on one side and all the sugar on the other side. And we can't do that unless we expend energy from outside the system. And that's exactly what this pump is doing inside the ink machine. It's injecting useful energy, or thermodynamic free energy, into the ink water filter system to sort it. More mechanistically, this big beefy pump is just shoving an ink-water mixture at high pressure into this filter. The water goes through, and what's left over concentrates into almost pure ink. So we're basically squeezing water out of ink in this machine, so that the pure water and the leftover ink can get separately re-injected into the tube. As we just spent way too long calculating, we have to expend energy to do this. By separating the ink and water, we're actually reducing the entropy of the system, and this costs energy. In this case, we can measure the energy being used by the pump very directly, and that's quite a lot. This is nominally a 100-gallon per day RO filter as purchased. So very approximately, we're looking at about 5 joules of energy to extract 1 cubic centimeter of water from ink. And in bigger units, that's about 1.4 kilowatt hours of energy per cubic meter of water. Of course, there isn't a cubic meter of water in here, but you can imagine that it takes that much power to cycle it until we get a cubic meter through. This isn't really a filtration process. Yes, technically, we're forcing a mixture through a filter of sorts, where pores don't let the solute through, but it's literally at a molecular scale, and that means we have to use more complicated physics. The physics of osmosis is thermodynamics, entropy, and at the end of the day, statistics. There's absolutely nothing. There is no law of physics preventing me from picking this up and shaking it until all the ink separates at one end and all the water separates at the other end. But am I going to be waiting like a really long time for that to happen? Yeah, in a system of 10 to the whatever many particles, it's just not going to happen.